Alright, here we have the probability that a male is colorblind is 0.042. In a group of 53 males, find the probability of the following, that exactly 2 are colorblind. I don't know how accurate this probability, the 0.042 is. This is just, I think this is an example I copied from the book or something like that. But regardless, we're saying this is a flat probability. It doesn't depend on whether or not other people are colorblind. It's just there's always a 0.042 chance. That's the probability. We have 53 males, so this is our number of trials rather. This would be our probability. And if we're saying the probability that exactly 2 are colorblind, we get, well, I guess first off I should say, if I'm defining p as 0.042, and that's the probability that somebody's colorblind, then I kind of made the implicit assumption that a success is colorblind. So before I start counting things up, I should make that make that note. So n is 53, p is 0.042. And x, we're saying the probability that exactly 2 are colorblind. Since we're counting colorblind people, I don't need to do anything weird with that. And we get x is exactly 2. If I wanted to swap this around and have the probability that, a success being somebody not being colorblind, I would have to change my probability to 1 minus this number, and my number of successes to, it looks like 51. 53 minus 2, which is 51. Alright, so we end up with binomial. This is the probability that exactly 2 are colorblind, so this is going to be PDF 53.0422. Oops, didn't count my second. There. 53, 0.042, 2, close up my parentheses and hit enter, giving us a probability of 0.2725. The probability that no more than 3 are colorblind. So I'm seeing no more than 3 successes, so n equals 53, p equals 0.042, x should be no more than, let's think about this, 0, 1, 2, 3, 4, 5, 6, ... all the way up through 53. Notice that whenever I'm doing this, I always start at 0, because there is the chance that we have 0 successes. Don't get into the habit of always starting at 1, because that'll definitely cause you issues. Always start at 0 when you're counting successes. Alright, so the probability that no more than 3 are colorblind, well, we could go up to 3 being colorblind. So that means x is less than or equal to 3. And you'll notice this is exactly, it's this number or fewer. This is exactly the setup we need for binomial CDF. So the binomial CDF, 53, 0.042, 3. The probability that no more than 3 are colorblind is 0.8176. The probability that at least 8 are colorblind, again, n is 53, p is 0.042, and now 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I'm going past the 8 since the 8 is mentioned, all the way up through possibility of 53. If we want to say at least 8 are colorblind, that means we're talking about 8 or more. So the 8 through 53. This is where we need to use, I need to do 2 different things, because my binomial CDF, my cumulative distribution function, always tells me a certain number or fewer. So I can figure out 7 or fewer. I can figure out this number over here, and that number right there is going to be the complement of this one right here. So the probability that x is less than or equal to 7 versus the probability that x is greater than or equal to 8. So these are my 2 complementary events. So the probability that x is greater than or equal to 8 is equal to 1 minus the probability that x is less than or equal to 7. And this probability that x is less than or equal to 7, that's the thing I can find with my binomial CDF. This would be a n of 53, p of 0.042, and x 7. That would be the upper bound on the number of successes here. Notice that we're always kind of shifting over by 1 because either 8 or greater or 7 or fewer. That will partition our sample space. All right. So let's plug this into the calculator. 1 minus binomial CDF. 53.042, and 7 is the upper bound there. And we get 0.0016. So the probability that we get at least 8 people being colorblind in this group of 53 is 0.0016.